So yeah, the final talk of this session is by Michael on preliminary results from Planet 4.
Yes.
Which sounds like it's going to follow talks from preliminary results from Planets 1, 2, and 3.
Yeah, with the preliminary talks, the title preliminary results was very ambitious. So instead of that, I would just need to give you an overview, because we have not really much done yet. As I said before, we have not much funding space on work on this. I'm working 100% in a NASA project, and yeah, I have to squeeze off any minute for something extra. But thanks to Mac, things are actually going forward by keeping the interest live. And she also provided cool plots at the end of the presentation about what's currently possible. This is our science team. Kenny Hansen is a senior scientist with Anya and me. We're working a lot on the seasonal effects on Mars. So what on the polar caps on Mars, how things are vary, what we see in the surface with a high-res camera, which I will explain a little bit. And I just, of course, realized that this orange color is horrible for presentations. Okay, a brief history. I actually don't remember with whom Candy met. Maybe it was with Chris, how it all started.
Yeah, I was interviewing her for the BBC and we got distracted.
Yes.
I got told off for turning the interview into a discussion.
Right, yeah, but this is what really cool, because Candy already had half a ClickWorkers project put together, but they didn't have funding either to push this forward. So the chat with you and then this stargazing event coming up, this was suddenly rushing everything like a rolling motion. We had to do really fast because the stargazing event was coming fast. And so yeah, we had this target date for the deployment. So the input data source was the high-rich image data set. And for the interest of time, we decided to go live with unprojected image data, which means the image data is just square. It's easier to process and put on the monitor, but it's not projected to the ground coordinates of the planet, which will create some works for us afterwards. But at least we got some nice data out of this. So yeah, after a few rounds of GUI iterations, just things went live, and we had huge success with this first BBC event. By the way, one of the things how we, or me personally, got interested in this, I mean, most of the team here in the room is actually from UK, so I don't need to talk to you about the excellency of the BBC documentaries, but there was this one thing about math and how it relates to everyday life. And there was this episode where this math professor went with a bowl full of marbles around the street, and he would be asking 1,001 people how many marbles are in there. And the amazing thing is, which I never thought about, how this relates to actually data exploitation and the wisdom of the crowd effect, is that the average value is correct. It's like any person who looks at this glass full of marbles wouldn't know how many marbles are in there. But you ask 1,001 people, as you do statistics with an uneven number, your result is correct. I mean, the mean value. And this is so amazing. And since then, I'm really hooked on the idea that you can do awful lot of useful things with this. Okay, little words on the HIRAS instrument. It flies on a Mars reconnaissance orbiter, currently around Mars, still actively taking data, but constructively being cut by NASA regularly and doing more science analysis. So now they're doing more and more only operations to take data for the future. Currently, I believe it's still the largest camera that is flying in our solar system for surface ground analysis. It has something like a 0.5 kilometer telescope. This is just out of top of my head, so I didn't check it. It's roughly 1 meter long and 57 kilograms heavy on a satellite. That's amazing if you consider that each kilogram on a space mission costs about $1 million. So we have a highest resolution, 25 centimeter on the ground, but very often we would fly with bins. So that's how sometimes when you look at the data of Planet 4, they seem to have different resolution. This is when we had a binning mode operating because we, for some reason, couldn't afford a higher data rate. So far we have only between 1% and 2% of the Mars surface observed. So this tells you this camera is really made for targeted observations, areas of interest, and that also opened it up to the idea that first of all the scientists in geology or Martian geology and whoever worked on this, they had to sign up for proposing target sites. But then we also made it up to the public. So there is now public high wish sites where anybody who finds an interesting object in older images of Mars which have total coverage, like the MOC camera, the Mars orbiting camera, you could then apply for a high wish target, and most likely between 3 and 6 months later you should get your observation. If it's well reasoned why you want to have this, then anybody can apply for an observation of HiRISE. So that's why it's also now called the people's camera. It's very successful in this way. Martian polar seasonal activity, a quick background on this. So every winter up to 30% of the atmosphere, which is 95% CO2, freezes out onto the polar caps. We call this the seasonal polar cap. The special interest in our stuff was born by observation of fan-shaped deposits, dark stuff in the polar caps, and identification of the so-called cryptic region, which was visible by having a reduced albedo. So it looks darker, but then with the thermal infrared radiometer, it was discovered it still has the temperature of frozen CO2 ice. So that was kind of a conundrum for a while. We now believe to understand that it's the thin layer of dust that is thermally conductive with the CO2 ice that's lying underneath the dust. So that's why it's still cold, but has a darker albedo, which you naively would think, oh, it's dark, must get warmer. But if it's thin enough, it just stays at the temperature of the CO2. So that's kind of how it all was born, and these kind of images the HiRISE camera produces. It's not clear in all cases. Where's my pointer? Right. So these dark spots. So this is South Pole area here. We mostly are interested in these dark spots. I say a few slides further on what is actually going on here. We have also brighter spots or bluish spots where we think there is, for some reason, there's more CO2 that's with a higher reflectivity. The colors are false color made by an automatic algorithm to maximize information display in the color space, made out of several color filters, 3 color filters we have on HiRISE. And yeah, so these kind of images are produced. We have currently only South Pole data on the Planet 4 system. We in the future we would like to do the North Pole as well, but the North Pole is inherently more complicated also in terms of the understanding of it, because there the water takes part in the whole cycle of activity, while the South Pole of Mars is very few water only. So we think we can ignore the water and the physics, what's going on. Yeah, this is a zoom in, and you see here in this image, you see a lot of interesting things which we want to understand. We see here transitions of dark zones to brighter zones. We don't understand fully, is this only just dust deposit here from other fans here, but then why is there an abrupt change there? Do we have cleaning effects of dust, making maybe seeds for refrost of CO2 in the early spring when it's still cold enough that in the night you again reach deposition temperatures of CO2 out of the interface, that's out of the atmosphere. That happens in the beginning of spring, while in the summer later on in the night it's not cold enough anymore for CO2 deposition. So how all this changes over the season, how it develops, that's what we're interested in. And these images are gigantic, by the way, 10,000 pixels wide all the time. And in the length, we have the freedom up to the memory. So we can take 100,000 pixels times 10,000 wide, and it's like gigabyte size, each HiRISE image. But it's really whatever you need as an interest area to cover. You can make it as long as possible. Yes, and one other detail is here, these lines, we believe to understand that, by the way, I should say, all this area is covered in CO2 ice, which we believe is transparent enough so that sometimes, not in this one so much, you can see quite detailed things are happening on the ground. And this is either by a perfect conforming over freezing of the CO2 or by enough transparency of the CO2 ice. We're not sure yet how much, but we believe that for these effects we need sun ice to penetrate the solar radiation to penetrate the CO2 ice, and that's why we think it for some reason it has so much time and coolness over the winter that it becomes transparent. It basically cleans itself by freezing enough. All right, that's the South Pole coverage of the interesting data. The so-called cryptic region, I don't have a visual image for this, but this is, I think this is altimeter data. Okay, so the cryptic region is somehow in this area where, and we interestingly have fan activity, so these jets that come out, I will explain further. We have these two areas. This is borderline, and Inca City is definitely out of what we have defined as cryptic regions. Still, Inca City shows a lot of the same effects. So it's also an interesting area which we now try to separate a little bit to finish up data sets faster with Planet 4. So we filter now a little bit by region to have some answers for some areas earlier than for others. Yes, I think that's all for this slide. I don't know if this will work. So this is, yes, it will work. So this is how things change over time at the same location. And this L sub S number, in case you're not familiar with it, this is how we consider the seasonal progress of Mars. It's basically the Mars position in its orbit around the Sun. So the northern spring would be at 0 degree and the southern spring at 180 L sub S, solar longitude. And yeah, all these different wind directions, we believe that just depending on the season, there is maybe seasonal weather patterns, and we want to use these fan directions also for analyzing this and how they differ from the so-called global circulation model of Mars, which just has resolutions of 100 to 300 kilometers, depending on which model you use. And we know that, especially in the polar area, these winds can be quite wrong. So we're now also discussing with people who are interested to collaborate for so-called mesoscale modeling, where we take DTMs, so level maps, so topography maps, into account for hydrodynamical flow simulations, so that we would have, they call this mesoscale modeling, and we could compare that with these winds and maybe deduce when these jets of CO2 gas actually erupt, because we think they are happening very fast, and the HIROS observations always happen in the afternoon. So we also think they happen in the morning. So we believe we will currently have no chance to see anything live happening, which also would be hard to observe anyhow because you look from directly above. But we also think we are a bit too late. But maybe with mesoscale modeling and these fan directions, which is basically the wind that happened at the moment of the eruption of this jet, and then depositing the ground material on top of the ice. So with this and the modeling together, we hope that we can constrain the eruption time. Yeah, this is another beautiful example of the blue fans. And it's interesting how if I go back, here the previous shape is made brighter, which is why we think there's currently for us only two possibilities. Either we have some cleaning effect that this dust layer is so thin that it actually goes into the ice by being a bit hotter and makes then little micro holes into the ice, which becomes highly reflective, and therefore it in these color images shines blue. Remember, this is false color, so it's just increased for informational display in the color space. So if something gets brighter in the blue filter, then it just appears blue in these images, while it's not really blue. But we think it could get brighter by these self-cleaning effects. The other thing is what could happen, that it's not actually sinking into the ice. And the simulation of that is actually rather difficult, because these little seeds, they go into the ice and then have to melt the CO2 away, but then you increase the pressure, which immediately goes away from the ideal gas equation and so on. So we're not sure if it happens yet. We need to put some work in it. But the other simple thing that could happen is that all these dust deposits actually act like a grain for CO2 ice deposition again. And that also would make it exactly in the previous shape of the fan. So this is actually the so-called Kiefer model. He came up with the whole chain of what's actually happening. And if I go very quickly through, we have the CO2 frost, and it's dusty, and it's maybe inside with this physics which we think could happen. It's self-cleaning over the winter. So the winter is 6 months, so we have some time. The CO2 ice gets translucent. We have here now the translucent CO2 ice slab. And you have the solar energy going through the CO2 ice, warming up the ground. And this energy here makes we call it basal sublimation of the CO2 ice. So we develop a pressure underneath here from the CO2 ice, which is now in gas phase. Eventually, this will break through the ice. And this is a nice artistic display of how we think it could look like at the South Pole. It breaks through the ice, and this transports this ground material which was coming through the ice, so it's kind of loose, and it's also the previously deposited dust, because we know every year is dust in the atmosphere of Mars. So these gas streams which go to the fracture from the sides transport this, and that's what we deposit on top of the ice. And if you do this for 1,000 years, we believe that these gas flows not only do the transport to the surface of the ice of what was previously in the atmosphere, but we believe that these gas flows also erode actively. Because that would be the currently favorite explanation model for so-called spiders, if you have ever seen images of spiders. Unfortunately, I don't have an example of these. But there are structures that have spider-shaped legs. We call them Aranean forms in a more neutral language. And we currently have no real good feeling of the time scale. It could be 10,000, 10,000, 100,000 years it takes, because we don't know what erosional force we can reach with these fans. We have some simulations for these CO2 gas jets, but they're very rudimentary currently.
So can you get back that out if we assume particle size? Then you have a fan width, and so then you can, if you assume like how thick it is, you've got an idea of how, well, at least can do the simplest, how much gas pressure, how fast the gas will be going to pick up the
Yeah. No, sure. We even proposed that, but the full end-to-end model has a lot of parameters. I mean, you have how clean is the CO2 ice? What is the braking force to get actually through? Which means this determines how much pressure you store of the CO2 gas. So how much do you get in? And the braking, so the yield stress of CO2 ice itself, interestingly, is not even very well known. Nobody has very transparent, clear CO2 ice blocks on the planet, because they're very hard to grow. What you normally get when you buy CO2 gas ice blocks are these completely white, just pushed together. Basically, they freeze it out with flakes, and then they push it together until you have these blocks of CO2 ice. But transparent, translucent CO2 ice blocks are very hard to create. We tried it in the lab, and we grew within a day, we grew some millimeters. But it's not easy. You have to have a chamber, a dirty chamber, which can stand some dirt as well. That is especially designed for this, with liquid nitrogen cooling, and that has a lot of cooling plate and maybe also sidewall to simulate the cool temperature of the Martian atmosphere. This is also something we still want to do, but yeah, it's not easy. So we always look in the lookout for somebody who has a huge cooling chamber that is allowed to be dirty. That's the important thing, because sometimes the interface with the dirt is important. So we need to be allowed to put soil simulants into the chamber. Okay, so this is one of the simulations we had. I guess I'm running soon out of time, huh? Oh, okay, good. So my previous boss, Nick Thomas, I didn't put him on now, but because it was not with the citizen sciences, before just our physics. We did some gas jet simulations, and it's interesting that even the particle size distributions of this deposits is not very straightforward. So depending on wind strength, and if you have slopes, the bigger particles or the lighter particles get further away, which changes the physics that can happen on your fan deposits, because when you have different particle sizes and different densities, densities and distances from the source of the fan, you have different effects happening, because maybe your deposition is very thin, and then they would maybe clean up or attract new CO2 ice very lightly, or your deposition is very thick, and the temperature maybe now isolates itself from the CO2 ice, which means it might be not a cold trap for new CO2 ice, and then it would not get blue in the deposition. So it's all kinds of these different depositions will create all different things. And we have some effects like what we call double halos, which we don't understand yet fully, and they also only appear at certain times. But we believe that it could be the result of a complicated arrangement of the topography alignments, that these depositions of particle sizes are in a certain pattern so that we get rings of CO2 ice creation, things like that. So it's a big parameter space to check. Okay, this is our Planet 4 interface. I think, I have a feeling from what I've seen before that our project is maybe more one of the difficult ones, because we're actually asking them to map out what they think is the opening angle. So the base position is kind of easy, especially when you have several people doing it. At the end, the base position will be the center of a certain cluster. But the openings angles, I mean, this is really difficult. And this is, by the way, at the end here, you see how it slowly fades out, the density of the fan. This is where my simple task of image analysis algorithms fail, always to automatically securely identify fans. Because depending on the contrast function you have in the image data, which again depends on how clean the atmosphere is, or if you have a sandstorm or whatever, or how much binning you allowed, how much exposure time was programmed, your contrast function changes, which means also this decay changes, which means there is no clear function of where you can reliably say this kind of decay defines the end of my fan. So that's how I couldn't find a proper way. I think that's my excuse at least. So, so the interface has fans, blotches, and interesting features. Blotches, we believe, are happening when there is not strong enough wind at the time of eruption. So therefore, sometimes we really have a round blotch deposit around the base of where the fan erupted. Just it comes straight up and falls around it. So there was no wind at the time, and that we have blotch. So for the blotch data, we have a 2-axis diameter. And for these guys, we have the length, we have the opening angle, and the center position. And then we have a third thing, interesting feature, where people just deliberately mark feature, I think with a rough size as well, or isn't it? Does the interesting feature have?
Just position.
Just position, okay. Right. Right, so, yeah. I had changed this already to... Ah, no, okay, yes, I remember. So the output of it, I forgot to add the input. The input is the 385 high-res images, but because they're big, they end up to be 96,000 subframes of something like roughly 800 times 600 pixel in this interface we saw before. So 96,000 subframes for this. So that's the input. The output of the data, as I just said, is base coordinate of the fan, opening angle, approximate length. If no discernible direction, we mark it as a blob. And the coordinate of interesting objects. That's the output we have. Science goals in general. Locations of activity and how does it change over time. So as I just said, the activity changes depending on how much sun we have, how transparent the ice is. Maybe in a certain area, because of topography control, we get not as clean ice as somewhere else. So it will be different in different locations. We want the wind direction, we want to compare with the general circulation models and mesoscale modeling, already mentioned. And this could be a really interesting thing for machine learning, the interesting objects. Well, if we don't have a size, okay, thanks. If we don't have a size, maybe it's not so easy. I was just thinking we cut out the position of the interesting object and then run an unsupervised learning on this to see if there's any similarities of what have people marked. But, well, we have to come up with something. Yes. So, Yeah, so the upcoming tasks, I need to differentiate because of this projection, the geo-projection not having happened with the data. I have to distinguish with what we can do now, with what we need to first postpone after we have made the ground projection. So we can now do the activity locations over time and how they change with different locations on Mars and how it changes per location over time. We can do that because that's just one point. Is something a fan there or is not? And for interesting objects, one could do that as well. But yes, but for the other science goals, we need to first ground project the coordinates from the Zooniverse image ID, from Planet 4 image ID, back to the high-res, and the high-res image ID needs to be ground projected. So what we want to do is, with the same algorithms, I would ground project the high-res image ID. I would ground project an artificial image with the data from the Zooniverse. From the Planet 4, I would put it in an artificial image and then run it through the same ground projecting data, and then all the data from Planet 4 should end up at the correct position on top of the surface. I believe so. But yes, yeah. For example, okay. I already was speaking with the high-res people if they think we can maybe even make it part of the official pipeline somehow.
Because we have so do something like that.
Okay. Yeah. Cool. Would be very good to chat about that. Okay, yeah, and the last point is get selected for EMDA. This Mars Data Analysis Program. We have a proposal running too, that I and I think Anja also gets some time, so that we would have 30% of our work time to actually do more active work. We hope that in the next 6 weeks or so, we hope that we had a good case, because now that they always want to see preliminary work in the proposals, with having this data set being there's a lot of preliminary work done by all the citizen scientists. So we hope that this is a good case. Goals for the workshop. Yeah, I want to consolidate the cleanup procedures, which may be different for MySQL and Pandas. While I see Magnus using MySQL, I'm using Pandas, which is HDF5 based. But at the end, the cleaned results should be the same. Maybe the procedures might be different. The status definition, which is, this is the point where you say when do we finish an image? It's 30 counts or 100 counts, and the results are quite different. So we should maybe agree. I mean, we have now switched it to 30, but we have to come up with a way to say, is 30 really actually good, right? So that's what I meant with that. This Mac already seemed to be able to do. Maybe she's doing it in a hard-coded way, but so we should have a general conversion library, just a function which everybody's using, so that I hope we end up. And I think it's not too hard. We just really, in 1 day or so, we should be able to do that. I have 1 or 2 issues which I think could be potential issues, maybe from older times in the beginning of the database. We have to check with maybe Stuart or who can help me with that. Code repositories, we already started that today, and so this is cool with Stephen's stuff. There must be, for the surface-related stuff, common algorithms that are true for all GUI-based marking citizen science, and these I think we could share, because they should really doing the exact same stuff and have lots of fun. Just some funny numbers. I'm just impressed. This is my top 10 users. And what this is basically is, I'm just impressed, even if they're only image browsing, they have pressed more than 35,000 times the submit button. I mean, that's already some physical effort. That would be a fun task, by the way, to calculate the work. So this is amazing. And this is the definition of, depending on the definition of done, 30, 40, 50, 60, 70, 80, 90 counts per image. We are here with season 2 and 3. I should mention season 2 and 3 is the later years of the high-res observations, basically a different winter cycle. So we had a first run there, we tried out a lot. By the way, I forgot to tell you, Mac, that this is okay, the count is correct. We had a lot of more trial outs in the season 1, that's why we have much more data there. Season 2 and 3, we were a bit more confident what we're doing, so we started with that. So we are here at 96% or something done with season 2 and 3. Yes, this was interesting to me. We have a strong difference with not logged in people. If I would use them, my whole data set is 42% done versus 16 if I'm not using them. Or for season 2 and 3, 96% done versus 32 if I wouldn't use the not logged in data.
So, but also 2 and 3 was done, the majority of it was done during stargazing. So
Yeah.
there's definitely a motivation difference potentially.
I see.
We can think about.
Okay. And here's a fun thing that I call the turnaround, because this kind of motivation just created so much discussion that it was motivating enough for us that Kenny Hansen, the senior scientist, put in a request to re-observe it. Because everybody was thinking this kind of chimney or whatever, and on top of it, we have this effect that is it now negative or positive topography feature that depends on how your brain switches, mind switches consistently to the wrong way. This is really, I can see it correct. But so we made a re-observation with a higher resolution, and it's still a weird thing. It's definitely not a chimney, but we still have a weird pattern on the ground centering here is why these kind of might be results of activity like these ice deposits here that maybe make a forming of the surface patterns. It's still asymmetric, so it's still weird, but it's not a chimney. So, but that was a result that, oh yeah, and Max first ways. It's actually interesting that some did the opposite of this. So this is the Max code already being able to do.
Oh no, this is totally just all the annotations plotted on there. I've done nothing other
Right.
than plot
Okay.
it on the image.
Yeah, but you can see what kind of work they have to do and how it ends up. It's interesting that somebody did exactly the opposite. I wonder if that is malicious. I mean, how can you not see? I don't know. Okay. And here you can see how difficult it sometimes is. The contrast function is so small that, and the objects are too small. We constantly get questions, do we really have to mark all? And we always say, yes, please. So, and imagine that doing this for this, to mark them all. And some brave people are really punching through the fingers to get all this data done. And yeah, oh, sorry, that was my last slide. This was just the thought which we had before. Yes, the nonsense data. For me, it's not clear. Is the distinction clear for no marks created by image browsing, which would be bad, or by actually having nothing to mark, which is good, because then we have a filter for what is done. And this distinction, we had it and I think in your talk also, it's not 100% clear where you put there the cutoff. I mean, that would consist of having a known data set, which we don't have with this. I mean, and I'm not sure even 30 clicks of professionals help much there to distinguish between that. But that might be is a good discussion point for the week as well. Okay.
Thank you for that. It's great to see somebody. It's good that you set out what your goals for the week are, especially having fun. There's probably time for one quick question.